Hi everyone, and thank you for joining my talk about mollusk species diversity in the Antarctic. I'm Peter Schächinger from the Zoological State Museum in Munich, and I will present the topic of my master's thesis about a marine slug species endemic to the Southern Ocean. The Antarctic is a unique ecosystem. Its surrounding ocean is shaped by the temperature close to the pole, as well as the isolation from other oceans caused by the circumpolar currents that inhibit water exchange in depths of up to 1,000 meters. Even for benthic life, this inhibits distribution of planktonic larval stages. Another characteristic shaping benthic life is the Antarctic ice. Especially during the last glacial maximum, the surrounding fauna was decimated by ice shelves, and species could only survive in refugia or in deep-sea waters. From there, the Antarctic waters were recolonized, leading to many Eurobenthic species that can survive both in shallow as well as in deep waters. The recolonization led to diversification in the empty ecological niches after the Ice Age. Still, many regions, like most of the deep sea, are still unknown to us regarding species diversity. This study focuses on Tritoniella, a genus currently with a single valid species that until now was endemic to the Southern Ocean. You can see a specimen of Tritoniella belli from the McMurdo Sound here on the left. It mainly feeds upon the soft coral Clavularia frankiliana that you can see on the upper right. There it ingests the gymal alcohol it uses as chemical defense, making it unpalatable to common predators like starfishes and sea urchins. It gets preyed upon by the sea anemone Isotalia antarctica, you can see also here on the right. As a little fun fact, it survives about 70% of the encounters by either just escaping or getting regurgitated from the gastrovascular cavity. Tritoniella was first described by Eliot in 1907. He differentiated between Tritoniella belli on the left and Tritoniella sinuata on the right, both from the Ross Sea. Those figure plates show the holotypes of both species that were made available as pictures by the Natural History Museum of London. Eliot differentiated them on the position of the rhinophore sheaths, you can see on the dorsal front part of the animal, as well as on penis shape and the teeth of the radula. After extensive material of expeditions was made available, Weddell synonymized the two species to Tritoniella belli in 1989 because she could not clearly identify specimen to the two species due to intermediate characteristics in most specimen. We now guess that these intermediate forms did not belong to either of these species. Only recently, my supervisor Juan Moles researched the phylogeny of tritoniids and thus shed new light on the topic. Here you can see part of his phylogeny, made with nuclear H3, a mitochondrial 16S and CO1 sequences. It shows Tritoniella to be a valid genus as a sister group to Tohoina, a genus that lives in Arctic deep-sea waters. Further, it differentiates between Tritoniella belli and 5 other species. The species hypotheses were delimitated with various species delimitation tests. My aim is to find morphological and anatomical characteristics to distinguish among the molecularly delineated species hypothesis. Let's talk about the distribution. As a reference, you can see New Zealand on the upper left, as well as South America on the upper right. When Eliot first discovered Tritoniella, he did that at McMurdo Sound, down here in the Ross Sea. While most of our specimens belong to an area that is called the Scotia Sea and are found mainly on the Scotia Arc and its islands. The rest of the specimen of our study is found in the Weddell Sea, that is right below my video feed here, as well as here. On the next slide, I will mainly talk about our specimen found in the Scotia Sea as well as the Weddell Sea. While Tritoniella belli can be found all around the Antarctic continent, it looks a bit different for the species we found. I will start with species number 1 in green, which is a singleton that was found south of the Falkland Islands up here at about 600 meters of depth. This area does not belong to the Southern Ocean anymore, which makes this specimen the only one found so far, not in Antarctic waters. Species number 2, here in blue, is another singleton that was found at King George Island at about 20 meters of depth. Species number 3 has a wider distribution range, ranging all along the Scotia arc, close to South Georgia here, and has a depth range from about 150 meters up here and 750 meters down here at Discovery Bank. Species number 4 was found twice, once at South Orkney at a depth of about 300 meters, as well as on King George Island below all those icons here at about 20 meters, so rather shallow water again. And last but not least, species 5 in orange has a pretty wide distribution range all around King George Island here and all the way here to the South Sandwich Islands. Although we are still dissecting specimens, I still wanted to give you an overview about the different species. I will start with Tritoniella belli. It can be found all around the Antarctic continent and shows a very bright white color. Another thing is the white central ridge. As you can see, I put the holotype right below it, and especially in the anterior part of the animal, you can see similarities, both in the ridge that is connected to the rhinophores, as well as on the head, the second smaller ridge. Coming to new species number 1, which is the only species that can be found on the other side of the polar front. Its potato-like body, both in live as well as in preserved, is the reason why we will probably call it Tritoniella gnocchi. New species number 2, which is the second singleton. Its main characteristics are the huge knobs on the nodal margin, as well as the central ridge that is built of single knobs. Species 3 shows a wide head and a conical body. The main thing I wanted to show you here is on the live picture, where you can see the white pigments, both on the tubercles as well as on the rhinophore sheet, that are so typical for Antarctic mollusks. Species number 4 shows, unlike the rest of the species that are mostly white or translucent, a bright orange color. Next to Tritoniella belli, the biggest specimen we found of Tritoniella are species 4. Next to that, it shows a very serrated mental margin, as well as a crooked central ridge. And at last, new species number 5, which is the species that shows the highest similarity to Tritoniella sinuata that you can see on the bottom left. We are still dissecting more specimens to find more similarities between the descriptions and the specimens. With this, we might be able to re-establish Tritoniella sinuata. Next to morphology, we also have a look at the anatomy of the species. While dissecting the specimens, we focus first on the hard body parts, in example the jaws or the radula, and second on species-specific differences in soft body parts. One of those is the penis here. For the hard body parts, we are using scanning electron microscopy that we will start to use in the coming weeks. With that, we are able to see finer structures, like for example the teeth of the radula. While I can't show you any of our own SEM pictures yet, I will use figure plate number 4 of Weddell's 1989 paper. Here you can see the dachidians, the middle teeth of the radula, of 3 different specimens. While Weddell distributed those differences to intraspecific variation, we think that she had several different species in her collection. The radula in Tritoniella is rather white, next to the Dachidian. The first lateral tooth is looked at because of its differences, and afterwards the number of lateral teeth on both sides are counted, and they look like this. Although we still got some work to do, the results so far give me confidence of finding morphological and anatomical cues to differentiate between the species. I'm also confident that we can submit this in a publication early next year. With that, I would like to thank the Systematics Association to give me the opportunity to have a talk at the Young Systematists Forum. I would also like to thank my direct supervisors Juan Moles and Michael Schrödel for the daily advice they give me, and I'm sorry for stealing that much coffee in the morning. I would also like to thank the associations on the bottom part, as well as Nedida Wilson, Charlotte Seid, Andrea Salvador, Heike Wägele, Peter Brüggemann, and Amy Moran for giving me access to specimens, granting me with valuable information, as well as live pictures of specimens. The biggest thanks go to you guys for listening to my talk, and I'm really looking forward to hearing your questions and doing my best to answer them. Thank you.